Hello, good morning, good evening, good night, good afternoon. My name is Brian Carlat, and I will be presenting to you a paper called Reverse Engineering IoT Devices, Effective Techniques and Methods. So first, I do want to give credits and sources, right? So this paper was originally published in the IEEE Internet of Things Journal around the end of 2018. So the authors here, I won't list them by name, but I do want to also recognize them. One thing that I did not note in here is that I believe their home university was Ben Gurion University, and I believe that's actually run out of Israel. So without further ado, let's go ahead and jump into the meat of it. Okay, so background. So first, this paper was a really interesting topic, right? And kind of the whole brunt of it, or the bottom line up front here, is that uh, IoT devices have since been proliferated since they've come to market, right? And what you kind of see here in this first bullet is that the initial citation for the projection of IoT devices by 2020 was 50 billion, and that's in the paper, right? So I did a little bit of research myself, right? And things have changed since this 2014 projection, right? It's 2022. Come on. So that's since been revised down to 25 billion by 2040, which is a really interesting drop. Uh, and for those that are interested, I did put the link to this source in the at the end of this slide presentation, so it will be included if you're interested. But really, before I get off onto a tangent, right, the authors really wanted to hit on proliferation as a driving need to make uh, new security practices, right? They basically said that, hey, these devices are proliferating like crazy, right? And in doing so, we're seeing architectural changes in these devices, right? So, initially when these devices came out, they were all, microcontroller based, really simple embedded systems, right? There's nothing crazy, no RTOS, none of that. Um, but today, what you see, like with, for example, the device everybody knows, Raspberry Pi, right? It runs a simple Linux. Uh, so, right, all these devices that we're seeing now are typically full stack OS based. Uh, and the authors really wanted to find a robust way to evaluate the security of these devices, right? So they employed the black box reverse engineering method that we'll get into. Um, Now let's jump into really, I want to give you a quick overview of the paper, right? So a little bit more down, peeling back the onion here. Uh, the authors wanted to provide a systematic reverse engineering method to, let me caveat, wanted full stack OS IoT devices, right? So what they did is they applied this method to 16 commercial COTS off-the-shelf devices, right? They provided their obstacles, how they evaluated it, right? They discussed some common characteristics and flaws, suggested some theoretical exploits based off of what they found, and they offered some recommendations to the consumer and the peons like us to keep our devices more secure. Okay, so really, before I kind of dive down a little bit more into the paper, right, the authors did note for those less witting of what an IoT device typically looks like, right? So it's going to have some sort of embedded processor, right? It's going to have some sort of non-volatile memory. You could have some random access memory for, those computationally intensive kind of tasks, right? You'll have some sort of sensor, right, or coils, right, as we've been learning in our class. Uh, and you can have a user face, HMI, whatever you need, and then of course, your power supply and wireless and however you communicate, right? So one thing that I did want to note here, and you see this big red circle. Uh, so this is something that the authors are going to hit on. Uh, UART in particular was something that the authors found to be quite a huge vulnerability in a lot of these commercial IoT devices. And it's something that I do want to jump up in front of because, right, if for those who have designed PCB boards in the past, right, if you are going to uh, design in a JTAG or a, some sort of UART programming way to program with your processor, you typically remove that at production. And what the authors found is that this wasn't happening, right? And that in itself, you got easy access to your processor, to your non-volatile memory. I mean, that's a security risk, and that's something that we'll go a little bit into the findings with that. Okay, so embedded device software architecture. So what do these devices typically run on? So what the authors noted in the paper is that, initially up front, you saw a lot of no operating system devices or some partial stack OS devices running like a real-time operating system, right? Interrupt kind of base thing. Uh, but now, as the cost of developing these electrical components, these systems really have decreased, we've started seeing a lot more full stack OS devices being deployed, right? And of note, in the interesting assertion, is that the authors said that full stack OS devices are the only known devices to be targeted in the wild, and it's becoming increasingly more common. Really interesting assertion and something that I did not realize. Okay, so let's jump into the black box reverse engineering method that the authors put together. So really, step one is to inspect your IoT device, right? So, you want to open it up. How do you open it up? Where are the screws? Where are the mounting holes? Blah, blah, blah. Easy. Uh, so when you finally pop that bad boy open, what you want to do is you want to find where those critical components are, right? So your non-volatile memory, where is your firmware stored? And then you also want to find your debug ports, right? JTAG, if it's there, UART in this paper was a really big hitter, as I had previously mentioned. So kind of these examples that you see here in the bottom, right? So this is what a typical, SPI flash, right? This is where you'll find your firmware stored. The same thing with NAND flash, right? But the flash memory is really what you're typically gonna look for. Okay, so the second step of this reverse engineering methodology is to extract your data, right? So you've already found where the firmware is at. You're like, ooh, I think it's going to be in there. So what you do, right? Um, what you'll find is that in these Linux systems, you have a bootloader that loads the kernel, and the bootloader is going to pass the boot arguments to the kernel, and then the kernel transfers control to user mode, right? But the way that you can bypass that is by changing your boot arguments to a shell, to the bin shell library, and from there you can bypass the password. And this was actually something that the researchers ended up having some success with. Um, right. Another way that you can kind of get into the firmware, right? You can use physical attacks, right? So doing a fault injection, right? So actually physically shorting the flash module or the flash chip was proven to be effective, right? So it basically failed back into a higher privilege shell, and from there you could get in uh, with privileges to the firmware, and you're able to export it that way. Okay, so the data extraction part, actually obtaining the firmware. Uh, so this is the fun part, right? So the authors noted that there are a plethora of available open source extraction methods, right? So they went into two different ways, right? So if you're connected to the network, if you're connected to the internet, right, uh, go ahead and look up Netcat, BusyBox, File Transfer Protocol, FTP, and wget, right? Those were some open source methods that the paper referenced. and recommended looking into. But if all else fails, you're on a closed network, you're offline, feel free to look into UART. And then if all else fails, you should use a logic analyzer, right? But essentially, the authors really the purpose of this was to say, hey, look, just exfil to the device of your choice. All else fails, UART is a pretty good way to go. Okay, and finally, so the analysis stage, right? So you found where the chip was, you got the firmware off, right? So now it's sitting on, say, some laptop, right, or some computer, desktop, server, wherever, right? And you're ready to analyze this thing. So first thing you got to do uh, is to unpack this memory image, right? And the authors noted that binwalk was another open source method that works pretty well on most embedded file systems. And firmware mod kit is another effective method. Um, so as far as passwords, right, the authors noted that a lot of these IoT devices are using Descript and MD5 crypt as the most common hashing algorithms in these IoT devices, right? So the authors noted that you can use things like John the Ripper and Hashcat as open source password cracking tools, right? And you can find word lists and password generation files in abundance anywhere in the internet, right? It's quite common, not hard to find. Okay, so the authors took their reverse engineering method and they applied it to 16 commercial off-the-shelf devices, all in a pretty reasonable price range from 40, $50 to all the way up to 100 and 170, I think is the highest I see, US dollars. Uh, so, and you can see, the device type, right? They focus a lot on cameras, visuals, right? A couple doorbells and a thermostat. And you'll also see that the manufacturers themselves are pretty wide variety. A couple of them I not very familiar with, right? But I think most know Philips, Motorola. Okay, so here's an example of 8 devices and in the method and technique that they used to extract the data, right? Uh, you can see that on some of these devices, right, UART is has not been removed, uh, whether it be through marked pads, right, or unmarked pads, where you just hope someone's not going to know what it is. Uh, and what you also see here is that some of the passwords loaded on these are just, trivial, simple stuff, right? Maybe a little bit beyond just password 123, but I mean, these were things that seem to be pretty easy to hack into and brute force your way in. So the authors did note that they ran into a few obstacles while they were applying the uh, reverse engineering method. So you can see here, device 2, the bootloader was in a read-only mode, right? And the way that the authors and researchers were able to bypass that, right, they induced a hardware fault on the flash memory chip, which actually enabled the processor to revert back into a higher privilege shell, and the researchers were able to extract the firmware that way. You see device 5, the bootloader was password protected. They ended up actually having to pull out the logic analyzer for that one. Device 8 did not support network tools for exfilling files, right? So the way they got around that, they actually extracted the raw binary data itself just using the echo command through UART. In device 16, the manufacturer tried to obscure where the pads were, so they claim, uh, by putting excessive numbers of test pads. So the researchers noted they made a few discoveries and a few light bulbs went off. Right, so one of their recommendations was, hey, if you're going to encrypt your passwords, make sure that you're choosing the right hashing algorithm, right? So they basically found that half of the devices contain passwords hashed with Descript, and the other half used MD5 crypt. And kind of continuing from the last slide, what you see is that if you were using MD5 crypt, you it took 90 times better. I say better, it took longer to crack than MD5 crypt. So for remote access, the authors found that they could use Nmap to reveal that many of these devices had ports open that probably shouldn't have been open in a production tool or a production product such as SSH, Telnet, right? Uh, Another kind of alarming discovery that they found was that a lot of these devices had pre-configured, hardwired uh, configuration files to interface with the internet, kind of hard-coded and easily accessible through the device for extraction. Um, Kind of this third one here, to me this is a big one. Um, they found that three of the devices had their own private keys hard-coded into the device. This one just kind of makes me shudder thinking about. Um, that's just kind of cybersecurity 101. Don't hard code private keys, guys. And finally, here in the bottom, they actually found that some of the components and devices that may have been bought out and then rebranded. Um, so manufacturer A buys out manufacturer B. Um, Manufacturer A wants to keep manufacturing manufacturer B's parts, right? That's basically what this means, right? So that after that purchase, right, things weren't changed, um, and that's really kind of what they found. So the authors took their findings and kind of did some cool stuff here. So they pulled the Mirai botnet source code off of GitHub, and actually they outfitted it with new passwords on a closed network to kind of test to see if these devices were vulnerable. And what they found is that the botnet worked really well, and actually it seemed to outperform the original Mirai botnet, I believe they claimed. So they also did some other uh, pretty cool tests, right? They were able to SSH into some of the baby monitors that they were testing, right? Um, and they were actually also able to upload some custom persistent software data into Flash. So pretty interesting. So the authors did note some theoretical attacks based off of their findings and analysis, right? So basically they said, hey, this reverse engineering approach will help reveal when some IoT device that can be bought off the shelf has outdated firmware, it might be vulnerable to attacks, right? So, um, if some bad actor were to able to determine that, my smart doorbell was running an old version of Linux, um, it would be more prone to things like, say, SolarWinds attack or Log4j vulnerability, whatever. Probably not related, but you know what I'm getting at. Uh, so here in the second part here, right? So physical access is kind of what they're hitting on here, right? So when you're physically accessible, like a doorbell, security camera, right, you are more prone to being able to be tampered with. Um, and then finally, here in this bottom bullet, right, they also noted there's vulnerability, right? So if a bad manufacturer or supplier wants to kind of stifle the competition, right, you can kind of take your uh, competition's device, reverse engineer it, maybe find somewhere to change a 1 to a 0, and then break all hell loose and give your competition a bad name. And so the authors did provide some recommendations based off their research, right? So first and foremost, remove the UART ports when you can. When you're done with them, if you're going to go to production, if your design's finished, take them out of the design. Take them out. It's not hard. Get rid of them. Uh, Another thing they mentioned was to harden your bootloader security. Uh, make sure that the hashing algorithm that you use to set your passwords is a strong hashing algorithm, and make your passwords unique. Do not hard code them and replace them frequently. Uh, they also mention making sure to encrypt when needed, right? If you're using something sensitive, encrypt your data. And then finally, pen test the devices before you go to production. In all likelihood, this bottom one here probably would have eliminated a lot of these vulnerabilities should this have been performed by the manufacturers or designers. So in conclusion, right, the researchers found that economics have played a really important part in IoT security, right? The drive and the push to lower costs in these devices, you know, brought some sacrifices in security, or really they just kind of skipped over the security part as a whole. Um, a lot of these devices seem to not be designed with a cybersecurity mindset, right? If you're going to leave your UART port on there, it isn't a stretch to think that someone who knows what they're doing when they open this up and they see the UART port on there knows that that firmware and that processor is um, available for access pretty easily, right? Um, and finally, right, they basically showed that, hey, this black box reverse engineering method we created is a really simple way to accelerate an attacker's work to introduce new and sophisticated IoT cyber threats. So without further ado, that's all I got. I do want to note that on this slide, I've got the dataprot source that I mentioned in the first slide that was created here in 2022. Much better reference with IoT statistics than the 2014 Gartner source that the paper was pointing to. So please do take a look at it. Really interesting. So thank you all for listening. Hope you guys all stuck through it. Have a good one.